There you go.
Of the process of Q in theory. So, just to put everything in context, so what we're trying to understand here is the concept of variation. So we said the three principles of lead: reduction of lead time, reduction of variation, change to quality of life, improving quality of life. The understanding behind mathematical calculation, reduction of lead time could be as simple as just reducing the operation. But the decisions of how do we reduce the operation and how they impact and how can we model this and represent it in a way that it's understandable over a more complex system, over something that is beyond a Lego simulation or just a single unit process, a single entity process. That's basically what this is going to do. So I guess the relationships that were established in here is, this is what we're going to do. Take any process, take a bank, take anywhere where you imagine that you are in a queue, right? Anything. When was the last time you were in a queue? It could be yourselves waiting, standing, or it could be that you were on the computer waiting for something. When was the last time that you were in a queue?
This morning.
Trying to get into the bathroom, 3 girls.
Get into the bathroom this morning
Waiting at the red light.
at the traffic light. So, in any of these waiting processes, there's a unique characteristic. You're waiting because there's a certain point that can process no more than X amount of people, in this case. And going beyond that, it creates the effect of we need to get free of the time that we're using that service time to get the next person in line, right? The people in line could arrive at any given moment. Doesn't mean that if you arrive early or late, you would be served faster or slower. It depends on many things that are happening. So all the math that we're going to look at here, try to explain that part. These could be considered the people, us, this the thing we are waiting for. And this thing has a certain capacity, right? So what we're going to try to understand is what is the effect of if we were controlling us getting into that particular service we want to get in a uniform way, in a more equally distributed way, or if we were with a group, we were carpooling or we were doing something and out of the sudden we arrived to this particular place, like there's only one entity, and then after a long time, boom, 4 people at the same time. So understanding that helps to cope with how do we manage the entire process. What do we need to have to reduce the impact of waiting? Nobody likes to wait, and that's one of the ways is waiting. So we don't want to wait. That's the whole thing. And when we put this, and then again, another of this, and another of this, and another of this, how does that look on the big picture? So that's the whole thing. So we need to understand, these are the formulas that we're going to be using. All of this has certain principle. I'm going to explain the queuing theory later on. But as for now, you are clear with coefficient of variation, are you? Okay? Just a magnified calculation for the deviation that we have. And we all are aware of what is high coefficient of variation, moderate, and low coefficient of variation, right? Okay. So we're going to be using a lot of that. What we want to measure here is how things or how people get into the service and how they live. Okay? That's what we're going to use. So, what are we going to count? What is relevant? The first thing that is relevant is to count how much time we have in average between me, let's put an example, going to the bank. How much time is between me arriving to the bank and the person after me and the person after that person? Okay? And that for a specific period of time, let's say Friday, from 9 to 5. How much time between 9 and 5 did it have between arrivals of people? That's the first one, TA. Where do we have TA? We have right here and right here, okay? And we're going to see why. So average arrival rate is just the inverse, okay, of that mean time between arrivals, okay? Then the standard deviation, the subs A is just the standard deviation of arrival. So if we have the standard deviation and the T, then we calculate the coefficient of variation, right? So the coefficient of variation is of the inter-arrival time. All right? So that's how we magnify if it's high variability or small variability. So we do the very same thing that we have there for departures. Okay? So all that changes is just the index here. Instead of A, we have D, but it's exactly the same thing. How often in average we have time between departures? Okay, how often did I leave or the people left the bank? Then the average departure rate, and then the coefficient of variation. Is that clear so far? Because this is very important to remember. Okay? So this is the relationship. We're just going to connect two. Okay? We can connect n number of processes, entities, servers. There are many names we can put to this. So we have a server. Imagine yourselves taking a test, a clinical test. Okay? And you have to go from one lab to the next. So this is one lab, and this is the next test that you have to run. These are connected in series. So there's two steps. You have to go through one, you have to pass to the next one. Okay? And there's people behind you that have to go through the same process. So you have to wait, then you arrive, you get whatever process or whatever test you have, and then you leave. Okay? But because the other process is right next to it, when you leave, it's exactly the same as when you arrive to the next time, process. Okay? So this is what all that is represented. So what we have is rate of arrivals. Okay, average rate of arrivals for process I. This is process I. Okay, this is the processing rate, and then rate of departure. The rate of departure of process I is equal to the rate of arrival of process I plus 1. Okay, so the big advantage of doing this is that that's the link that we're going to have between processes. If I connected I plus 2 here, the rate of departure of I plus 1 would equal the rate of arrival of I plus 2. Okay? So, and that goes all the way. So that's pretty much what this right here is saying. The time, average time between arrivals of process I plus 1 is equal to the average time of departures of process I, which is the previous step. Is that okay? Same relationship for coefficient of variation. Coefficient of variation of arrivals for process I plus 1 is equal to the coefficient of variation of departures for process I. Okay? So all this means is whatever leaves in the numbers, whatever leaves equals the arrivals for the next process, for the very next step. So, this is what we are going to use. We are going to try to characterize the variability and the impact of this variability if we have, you remember a couple slides, constant flow or of arrivals, or if we have like clusters coming at very different times. That's what we're going to try to do. And then, what is the impact that that has on the utilization of the process? Okay? So, now we have to consider the third element. We are waiting. We don't know at what time we come, but we get there. If we are waiting, it means the process is busy. Okay? So we have certain measurement of when we arrive there. Then the process here is working. But the process could be idle if there is no arrivals. Do you agree? If there's no customers at the bank or there's no people to be tested at the hospital, this thing right here, it doesn't matter how long it takes to process, will be idle. There's not going to be work at all. So that's the utilization part that we're going to measure. Okay? Then once it's occupied, then we will measure what is the effect that that has for departures. Okay? So this is, we're going to consider the assumption that we have equal, identical, or similar machines, M, so that's just the quantity. So the utilization, okay, mathematically will be calculated by the rate of arrivals divided by the rate of the processing time at the station, okay, raw processing time. That relationship will explain the utilization. Does that make sense? What do we look for in a utilization rate or utilization number? We look for percentage, right? As high as possible. So if this thing is close to 1, it means it has very high utilization. If it's close to 0, very low utilization. If it is always at 1, what happens? You don't have any more capacity, and there's one effect that starts happening with the Q. What happens with the Q?
It's bigger.
Starts growing, right? How big then that Q get? It depends on the system that is being modeled, but it has a capacity as well. If it is a parking lot, if it is a physical space, that Q will grow as big as the space permits, right? So this is important because this is the way that we can measure bottlenecks, okay? So I guess it's a good time to bring in, how many of you already had a chance to go through the goal? Just leisure time, the goal, the book, the goal from Eli Goldratt? Well, there's, huh?
I said there's no leisure time.
Okay. Whenever, it's a good book, okay? It's a good reference, and it has a lot of metaphors for this type of things. So, one part of the book says, this is the story about a guy that is a plant manager. And he's trying to find ways to bring back to life his factory because he's about to get closed. So to go straight to the point, at one part of the book, he has some leadership role with the Boy Scouts or something like that, and they went on a hiking trip. And he came up with this metaphor as they were going through the trail. The kids, it was, I don't know, a group of 10 kids, they were just all going together. And he was trying to understand the pace that the group had. And then he started seeing that the group started to split. Instead of having one, and the rule was never split. So they started to split. He had to say something so the group would reunite. And that brought this idea to his mind, like that's how you explain variation. He said the group splitting up because there's a group of kids that can walk at a certain speed, and then the rest of the kids may be able to walk at a certain speed, but they're being held by someone. And this kid, his name happened to be Herbie. So what he was trying to explain was how bottlenecks work. So he said, if I put Herbie to the front of the line, the whole group will be together again. If I put him all the way to the back, then the rest of the kids would go ahead, maybe, but they will leave Herbie behind. So Herbie was the bottleneck right there. And basically what he was trying to say was that Herbie was the pacemaker for the group. He was the one that was setting the pace of how fast this group could walk. So the utilization of a process, going back to our topic, is important because the utilization of a process can determine the pacemaker or the bottleneck. Okay? According to factory physics, with a more mathematical calculation, the bottleneck will always be the process with the highest utilization. The bottleneck will be the process with the highest utilization. So how do we calculate that? We have it right here. So, just to put a little bit more math, and you don't need to memorize any of these more extensive formulas. We're gonna go back once the example comes through, but what this means is the coefficient of variation, the square of the coefficient of variation of the departures based on this relationship right here equals the utilization squared by the coefficient of the raw processing time squared, coefficient of variation plus 1 minus the utilization of the coefficient of arrivals squared. So that's a relationship that we have between arrivals, process, and departure. Okay? So this is the way we would magnify variation. This is for a single machine station. If we had a multiple machine station, we just have to add this component right here, which is how many machines we have in the station. So that changes a little bit the formula, but it's exactly the same. Just substitution of this, whatever we have the numbers. Okay? So not try to get you to grasp the whole thing in these two formulas. It's just that's how we connect the variation and how we measure the impact of variation for the whole stream, for arrival, process, departure. Okay? So we have a segment right here that is going to have arrivals, processing, departure. We can measure it this way, and then we can jump into the next and measure arrival, process, departure. We can make those boundaries, go to the next, arrival, processing, departure, and measure it that way. The good thing about this is, if I get the data from here, I can use this portion of departure to get the arrival here. So all I need is just one or the other, the arrival or the departure for the subsequent processes, so I can connect.
When you're working on a batch, is it when the entire batch is processed and moves on?
That's a good question. It will come down the road how you work with batches, but here we're assuming that it's aggregate units. So we're measuring, if it's a whole batch, every time something arrives would be the batch, if it's consistent.
Okay.
If the batch changes in its size, then we would have to consider the units that arrive individually. Okay. Any other questions? Okay, so this is the most important concept that we need to get for how to measure variation. So we were mentioning about that relationship, okay? This is process, arrivals, departures, okay? And this is how we have the impact if it's low variation of arrivals, high variation of arrivals, okay? Low variation of arrivals, high variation of arrivals. High variation of departures, high variation of departures, low variation of departures, low variation of departures. Remember, we're measuring what? We're measuring the coefficient of variation, all right? So this is, and you remember when coefficient of variation was high and when it was low, right? It's same here. High whenever it's larger than 1.33, moderate when it's between this and 0.75, and then low when it's below 0.75. Okay? So if we have a high utilization station, okay, most likely a bottleneck, the propagation of variation is going to happen in this way. We have low variation of arrivals, which means pretty much an even, steady, calculated, which could be an assembly line, could be something that is more planned, okay? Could be, I don't know, I've been to, for example, on Thanksgiving, when you line up for Best Buy, they won't let all the customers go to the store at the same time. They kind of try to keep certain distance between the customer in line and the next one. So they make you wait, I don't know, 5-10 minutes. So that would be a more controlled process of releases. So the departure is with low variation. On the contrary, if we are like a lot of processes in life, at a certain time we arrive all together, and then there's a lot of big gap in between, and then 3 items arrive, and then not so long, only 1, more kind of random or higher variation. In these 2 cases, if, and again, I'm saying the scenario is the process has high utilization. Let's assume it's a bottleneck, okay? If the arrivals are this way, and we have very high variation in how we process things, okay? Departures are gonna be high variation, okay? So what's the takeout from that? What's influencing departure coefficient of variation is not the arrivals, is the process, okay? That's in high utilization stations. You see how that proves the theory? We have low variation of arrivals and high variation of arrivals. Low variation in both processing. What happens to departures? Low variation. So, if we want to reduce variation in a process that is a bottleneck, where should we focus? Should we focus in the queue, or should we focus in the process? In the process. Is that okay? Now, the conditions change when that particular process is not high utilization. Okay? Again, same conditions. Okay? Low, high, arrivals, high, high, low, processing leads to what? Low departures, high departures, low departures, high departures. So what is dictating the variation in departures here? This thing right here. So when you're not working in a high utilization station, the variation is going to pass on from how the items arrived. Does that make sense? It's kind of logical. Okay? If you have in the bank 10 people, 10 tellers, and there's kind of constant or you can find in any given time these 10 tellers with a high capacity. Each teller has a different processing time. Okay, they're not standard. They might be high variation in what they do, and not all the customers will require the same services. The departures, the rate at how you're gonna see people leave the bank is gonna be determined by basically how they arrive, as long as they do not exceed the capacity of the system, right? So as long as there's less than 10 customers in any given time in the bank, you're gonna see them leave pretty much similarly as the way they arrive. If we reduce the number of tellers to 5, and we keep the same rate of arrivals from people, what's going to determine how they leave is going to be the ability of these people inside the bank to get the people out.
Can I mention something? Let's assume there's a class that takes a lot of your time. High utilization. On top of that, if you put high variation of things coming in terms of assignments and demands, what does that create for you? Just an example of, I want to see that, right? So what have we done? We said, in my class, let's drop that utilization to a low utilization. Don't finish this semester. If I have low utilization and then I have low, what is it, variation in terms of things coming in, what does that do now? It creates low variation, which is really another word for stress. You see, does that make sense? Okay.
Are you familiar with the, what Kroger implemented on their process where they have the cashiers, how many they need at certain times? Is that what they're doing up there with, they're monitoring their arrival rate of their customers coming in?
That's exactly what they're doing, okay? Except what they're doing is they don't want for you to have a very high, it's a little bit of a different concept. When, I don't know, what time is it, 5 o'clock in the afternoon? What time is it that you have a lot of people at the grocery store, right? You have very high utilization. There, and all we know is the number of people coming in could vary a tremendous amount. And what that creates, very long lines. And you have very dissatisfied customers. So that by the time you leave that system, you have people that are, ooh, you know, this took me a long time. So that is what they're trying to avoid. So this is not only about processes, this impacts our personal lives, it impacts our processes. This is a fundamentally different way of thinking about, now, let me ask you, when was the last time you told your spouse, yeah, Jeremy, I'm looking at you. When was the last time you told your spouse, I said, be quiet, or you know, something like that? When was that? What caused you to behave like that? Not high stress. High utilization, because if you were at a low utilization, you would say, oh honey, it's okay, I'll take care of it. It was that high utilization and you felt that things were out of control because things were hitting you with a tremendous amount of variation. This is not only true for you, it is true for processes in general. And I would assume that there is a tremendous discrepancy between processes at ORNL or Y12, and let's not talk about Rubbermaid for a minute, that I have seen processes that are extremely low utilization, but then I have seen processes, oh my God, that are extremely high utilization. And I've found that there's a conflict between this group and this group. Why? It's not because I hate people, oh, I hate Jeremy, I hate you. It's not about that. It's about this concept. So you can take anything and break it into this concept and gives you a different way of thinking about it. Is that okay?
All right, so here's one example. Going to the batch arrivals, okay? So we have 16 jobs arrive once per shift, and the shift is 8 hours, okay? And we can assume that because it arrives once per shift, the coefficient of variation of arrivals equals 0. So no variation at all, okay? But the inter-arrival time for the first job into the batch is 8 hours, okay? For the next 15 jobs, it remains at 0, okay? So we follow through this. We said the inter-arrival time is 8 hours, okay? That we have there. And we have 16 jobs, so the first one plus the other 15, it's 0.5, okay? Every 30 minutes. So that inter-arrival time is 30 minutes. If we use the other formulas, okay, to calculate the variation or the standard coefficient, this is the variance here. we have that variance equals 3.75. Okay? So therefore, coefficient of variation squared is just 3.75 divided by 0.5 equals 15. Okay? So what does that mean? In general, if k equals batch size, so the coefficient of variation squared would be k minus 1, which is 16 jobs minus 1 equals 15 at coefficient of variation 0. All right?
All right, so what is it, Nick, can I ask just one, so
Yeah.
what does all this mean? I mean, yeah, you know, there's equations. What does it mean? It means that if I were you, I would say, my God, I need to, if I want to distinguish myself from other people that are working close to me, I need to understand that, I need to understand CA, whatever CA is. CA is what? Coefficient of variation, 1. They may or may not understand what coefficient of variation is, but you do. Okay. I need to understand the variation in my departure time. I need to understand my variation in my process time. Now those 3 variations, everybody looks at numbers. Don't you say on the average, on reports that you have written in the past, don't you say on the average, we have 12 people showing up at a particular term. Would you do that?
Yeah,
Now, you and I know that that makes no sense. Average makes no sense. Average is a figment of imagination. There is no 12. And if you take 0 and 1,000,000 and I say the average is 500,000, watch this. One number is 0, one number is 1,000,000, and so there is no 500,000. You either have 0 or 1,000,000. So this average, the number that you use, is a figment of an imagination. It's a fake number. It only makes sense if everything is close to, what is it, 500,000, okay? If I was 499, 501, 499, 501, that 500 makes sense. But we take these extreme ranges, we average them out, and we say, let me ask you this. On the average, do your family like you? Yes or no? Yes? You're hoping, if they like you, that the variation around that like is very small. I like you a little bit less, I like you a little bit more, I like you a little, it's all around like. What if you took somebody and said, I hate you? Oh baby, I love you. There is no love here. So this allows you to understand the coefficient of variation. So if I were you, I said, I don't care about any of this stuff. I need to find equations that tell me about CA, that tell me about the process time variation, that tell me about variation associated with the departures. These 3 variations are connected with each other. Where? It has a different relationship if it's high utilization, and if it has a different relationship if it's low utilization. It determines human behavior, and it determines the process time, its process or system behavior, right? Now, just that thought, with the ability to calculate the variation, just like he showed you, the variation is what? 15. Oh my God, what does 15 mean? It's pretty high, isn't it?
Yeah.
In your previous discussions at work, would you not have assumed a coefficient of variation of 0? Yes or no? If you don't even mention it, what does that mean? And it is that silent killer of processes, that variation. So my thought process here is, I get this idea, oh my God, there's a system about this, I understand variation. I now, Enrique is showing you, hey, here's an equation, here's an equation, here's an equation. You don't have to memorize this, but you have to know where it is in the book or in the slides, whatever, all right? And then you, when it's appropriate time and you start analyzing it, you say, oh, let me quickly look at the variation. And if the variation is like 1, okay, you ignore it. But if you find that the variation in a process that you're looking at is 1,000 million, all right, You can't ignore it. You're simply saying, I can't see you, so therefore you're not there. That's what it is, right? So focus in on your C's, on what Enrique is telling.
So I guess what Dr. Son is trying to mean is like, for example, in here it says that the jobs arrive at the beginning of the shift. Perhaps the analysis suggests that the entire process should be designed for jobs that arrive every half an hour, because that's the inter-arrival time, the 0.5 right here. But in reality, it's not that. In reality, is that we have everything arriving at the beginning, and then we don't have anything arriving later than that. So how should we manage that? So the effect is that we made the assumption that there is no variation there because we have everything consistent coming in. But at the end, math shows that we have coefficient of variation of the square of the coefficient of variation up to 15. So batch arrivals, the conclusion here is that the actual number, and that later on, and I think in the book you can see that there's a simulation that actually calculates that and gets how batch arrivals create the effect. And it's a number in between 0 and 15, but still is not 0. Okay? So that's the whole point. So batch arrivals increase variability. So we are gonna kind of jump into another topic that complements the previous. So I think it would be appropriate if you want to take a 5-minute break so that we start with queuing theory and then we go on. Oh, thank you.